In the second part of chapter 2, I try to summarize the mechanics, the mathematics that underlies the description of the so-called McConnell-Bloch equations, which allow one to derive such things as line broadening, line narrowing, coalescence, and all these things on a more serious basis rather than pure empirical discussions. Now, Peter Hoare has collected a remarkably well-selected set of examples of chemical exchange. I would like to start with the example that Peter mentions as one of the last of his illustrations, because I think it's one of the most important ones. Also, it happens to be discovered in Switzerland at ETH Zurich by Kurt Wüthrich, whose name is I wrote out here. And Kurt Wüthrich got a Nobel Prize for NMR of biomolecules. This was in 2002, if I remember correctly. And he once said in an informal lecture that the effect that I'm going to explain to you now was one of his most important discoveries. And I would tend to agree with that judgment. He has done many, many things, but this is very intriguing. So what we're talking about is tyrosine, the motion of tyrosine, which occurs in proteins. And in fact, the side chain of a tyrosine, you have the backbone here, then you have the CH2, and you have a phenyl ring, which is a para-hydroxy group. So that's tyrosine. And of course, there are 4 protons in positions 2, 3, 5, and 6. If the tyrosine is rotating freely, as it would be in solution, then you would expect protons 5 and 3, which are in the ortho position, to have the same chemical shift, and likewise you would expect 6 and 2 to have the same chemical shifts. Now, Wüthrich did not record these spectra in free solution, but he considered tyrosine, actually number 35, which is in this protein, which is called basic pancreatic trypsin inhibitor, which has about 70 or so amino acids, and number 35 happens to be a tyrosine. There are other tyrosines, but this one is particularly interesting. As you can see, you can record spectra of BPTI from very low temperature, just above freezing, to very high temperatures, in this case without significant denaturation of the protein, which is not obvious. Many proteins would decompose, but this one is quite happy. And you see that at high temperature, you see the effect that I sort of hinted at, that protons 2 and 6 occur at a given chemical shift, about 7.2 or so ppm, whereas protons 3 and 5 give rise to a single chemical shift, which is actually split into a doublet. And the doublet actually comes from the coupling between the ortho and the meta positions, but that's not relevant to today's discussion. As you lower the temperature, which is easy to do, you find that the spectrum gets more complicated. And the first thing that happens, going from fast flipping to slow flipping, is that this broadens out, and then it splits up in 2 distinct resonances. One corresponds to the ortho position, the meta position 2, and the other corresponds to the meta position 6. So these 2 protons now have vastly different chemical shifts. That comes not from the tyrosine itself, but from the environment. It turns out that the protein environment here is distinct from the protein environment on the other side, and therefore these 2 protons are exposed to different local fields and have different chemical shifts. Something similar happens if we look at protons 3 and 5, so those are the 2 in ortho position, which I've now put in a square box. So at high temperature they are essentially degenerate. The doublet structure, as I said, is irrelevant now. And when you go to lower and lower temperature, they broaden and they split up into 2 distinct resonances, 5 and 3 here, 2 distinct doublets. Now the remarkable thing is that this happens, although the temperature scale is the same, you see that the coalescence for the 2 protons that are close together at low temperature occurs at about 40 degrees or so, whereas the coalescence for the 2 protons that are far away from each other occurs at about 60 degrees or so. That is simply, in fact, a verification of the laws established by Bloch and McConnell and can be calculated with the type of theory that I explained in the previous part. Actually, beyond a simple illustration, this picture has dramatic implications for protein and the understanding of protein dynamics, because this interconversion really supposes that the protein flips, as it is drawn by this line here, that the aromatic ring of the tyrosine actually flips over. Now that means that it must be standing upright, perpendicular to the plane of the paper, maybe for a very short interval, but it has to be able to flip over from the flat position one way to the flat position the other way, so that the positions of 2 and 6 can interchange, and 3 and 5 likewise interchange. Now that implies that the protein must be dynamic, that it must be able to breathe, as it were, in order to leave sufficient room for such an exchange process. Indeed, quite a remarkable observation. Now there are more basic examples, and this one was probably already discovered in the 50s, possibly at CERN by the very early investigations of Damati and others. Now we are talking about ethanol. It turns out that if we take the multiplets of ethanol at neutral pH, so this is at pH 7 here, then we can not only see the conventional triplet for the methyl group that is due to the neighboring CH2, but the CH2 is not simply split into a quartet because of the neighboring CH3, but it's in addition split into a doublet because of the neighboring OH. Likewise, we can actually see this OH proton here, and it is split into a triplet because it is coupled, scalar coupled, with the neighboring CH2 group. Now it turns out that you only have to add a very minute amount, trace amount of acid for this effect to go away. And then we observe a simple singlet here, and the multiplet of the CH2 group collapses to a simple binomial quartet. So the question is, why do we observe such a collapse in the spectrum? The answer is, if we consider a simple molecule, a monomeric form of ethanol, we may have a proton called A attached to it, which may well have a polarization which is parallel to the magnetic field, which we could call alpha. And the external proton, the one that comes from the water or from the acid, would be called proton B, and that in this hypothesis has the opposite polarization, namely beta. If these two exchange, and that is exactly what chemical exchange is all about, then of course the B proton will become part of the ethanol molecule, but it will retain its beta polarization, whereas the A proton will go out into the medium while retaining its alpha polarization. From the point of view of the CH2 protons here, that's these ones here, which we find here again, it looks as if the neighboring proton in the hydroxy position has flipped from alpha to beta. And this flip can occur at a phenomenal rate because acid-base reactions are extremely fast, and therefore they lead to a collapse of the multiplicity of the CH2 group. And that is exactly what we see here. You will recall that this line here can also be broadened because of exchange between OH and the environment, so it's not easy to observe such a sharp line. But normally we just see this part here. We do indeed see a quartet here and a triplet here. One of the best examples that Peter Hoare has cited in his book, actually due to David Grant and others in Salt Lake City, is the example of cis-decalin. Cis-decalin can be drawn as a flat molecule, so this is not aromatic, but it still can be drawn like this. And if we do it that way, we can number the positions, so we're talking about the carbons or the protons, in this case the carbons. This is the conventional numbering of this molecule. And if we draw it like this, it is not surprising that the symmetry makes that the chemical shifts of these two sites are identical. And you can go further and you see that the chemical shift of this side should be the same as this side, and this side should be the same as this side. And then, of course, the other sides are distinct, so we find that these sides are all distinct from the previous ones. And the net effect is that at 46 degrees Celsius, when the molecule can be essentially considered as interconverting so fast that we allow to draw it on a flat plane, well, at that temperature we only have one peak that corresponds to these two bridging carbons, We have one peak that corresponds to the 4 carbons that I have circled here, and there's one peak for the 4 carbons that I have put in square boxes. So far so good. Now it turns out that if we go to lower temperature, from 46 to 16 to minus 12 to minus 29, then the situation becomes more complicated, and a little bit like in the case of Wüttrich's tyrosine, we see that these lines split up. And the reason is that at lower temperature we now have to consider these molecules as separate rotamers or separate conformers, and that the symmetry is lifted. So we still have a symmetry between these two, and likewise between these two, that has been preserved, and indeed that line doesn't move at all as a function of temperature. But we see now that, for example, this line, although it's the same as this line, it is no longer the same as this line and no longer the same from that line. So we see 1 and 5 which still pile up together, and we have 4 and 8 which are still degenerate, but they are no longer equal. However, if we warm them up, so you see that 1 and 5 and 4 and 8 are here, and they will tend to coalesce and end up with the positions that I have indicated previously. Now we see that there's here a twofold coalescence. We notice, by the way, that in this case the coalescence occurs at about the same temperature, and that the splittings between these two and these two by accident happen to be about the same. This is a very good example. In fact, at the beginning of this chapter I spoke about the interconversion of cyclohexane, which, as I mentioned, is too fast, where you see when you make cis-decalin it becomes slow enough so that you can observe it at room temperature or in the vicinity of room temperature. The next example is much more sophisticated. This is known as bulvaline. It's one of these molecules that was probably designed in order to get into the Guinness Book of Records for maximum complexity, and in fact all we have to remember is that we have a cyclopropane unit where we have 3 positions, carbon-13 positions, which appear here, and we have a bridging position which is a lone position here. We are of all sorts of rearrangements, so-called cope rearrangements, where the double bonds travel and the cyclopropane ring opens up. I will not give you a lecture on organic chemistry, but you see that this cycle here turns up here, and so on and so forth. And in doing so, for example, this site here, which was the isolated D, now becomes a site A, which is typical of the environment of cyclopropane. And so, indeed, there is an interconversion between A and D. And in fact, the entire process can be summed up in this sort of topological graph, showing that D goes to A goes to C, C to B, and B remains in part equal to itself in the course of this rearrangement, this cope rearrangement. Now we see again that at high temperature there is only one position, but as we lower the temperature it splits up into many lines, and we can of course precisely determine the exchange rates of these processes by doing an analysis of these line shapes. So the next example in Peter Hall's book should be more to the liking of people who are interested in organometallic chemistry. He is interested, or explains, cites an example of this ruthenium complex, where you have the tricarbonyl ruthenium, which is sort of hovering over this cyclooctatetraene ring, and in doing so can find itself attached to different positions. So we have 2 ordinary double bonds and this delocalized affair, which is the location where the ruthenium is most strongly attached. And it turns out that the ruthenium is not very tightly bound to this and can move a little bit like the hands of a clock around a circle. And in doing so, at high temperature we have a single line in carbon-13, but as the temperature is decreased it splits up into a manifold, and you can see that again we can draw topological diagrams which show the exchange rate between these 4 different forms. It turns out that the question here is whether we have a 1-2 shift or a 1-3 shift or a 1-4 shift or a 1-5 shift, and that these spectra allow you to rule out some of these mechanisms and choose one of the ones that is correct. So the next example in this chapter has already been discussed in an earlier chapter about scalar couplings between spin 1/2, such as carbon-13, and quadrupolar spins, such as lithium-6 in this case. So lithium-6, to remind you, has a spin of I equal 1. It therefore has three possible states, m equal +1, 0, or -1, and consequently the neighboring carbon-13 here, if there were only one lithium, would be split into a triplet with 3 equal intensities, so this is known as a non-binomial triplet. But as we have discussed before, it turns out that lithium can build a tetrahedral structure, and that we have these tertiary butyl molecules, which groups which can attach not to the corners of this tetrahedron, but to the faces in the middle of each of the triangular faces. And when that occurs at low temperature, each carbon-13 will be coupled to 3 lithium-6, and that results in a rather peculiar non-binomial multiplet like this at low temperature. But the situation gets even more complex if we heat it up, so if we go from low to high temperature, because then it turns out that these groups here can move about from one surface to another. In fact, they can hop from one triangular surface to another, or if you prefer, they stay where they are, but it's the lithium cluster that rotates within the cloud of the carbon substituents. Whatever this case may be, it turns out that at 26 degrees Celsius we find that each carbon-13 is coupled not to 3 lithiums but to 4 lithiums, because all 4 lithiums, even this remote one, will at one point be close to the carbon-13 and have a stronger coupling. We see two interesting things. First of all, the multiplet becomes more complex, and also the effective scalar coupling, that is the splitting here between this and this, is larger than it is here. It is actually reduced because of the averaging. So I'd like to summarize chapter 4, the chapter that Peter Hoare dedicated to chemical exchange, which seems to be one of his favorite subjects and is indeed one of the key aspects of modern magnetic resonance. So chemical exchange effects in NMR can arise either from chemical or from conformational equilibria. In the slow exchange regime, NMR lines are simply broadened, and we can measure the exchange rates by looking at the line widths. Now, the difference in NMR frequencies between exchanging spins can be averaged by fast exchange. It is the magnitude of delta nu, that is to say the difference in the chemical shifts between the nuclei that are involved in exchange processes, relative to the exchange rate constants, that determines whether the exchange process is in the slow or in the fast regime. Chemical exchange effects give information on the rates and mechanisms of chemical reactions, molecular rearrangements, and internal motions. Now, most comments in Peter Hoare's book refer to chemical exchange between sites that are distinct because of their chemical shifts. But there are other ways of distinguishing sites, and one of them, for example, is quadrupole interactions in solids. Here at the École Polytechnique in Lausanne, we have spent years determining the spectra of nitrogen-14, which is a quadrupolar nucleus with a spin 1, and has a quadrupole interaction that ranges from 1 to about 5 megahertz. Now, in that case, we have observed exchange broadening effects between different sites that are interchanging at very high rates. So when the exchange rate is, say, 1 megahertz, that means the lifetime is on the order of 10 to the minus 9, that is to say seconds, that is to say a nanosecond, and consequently the N14 spectra are sensitive to processes that occur on that timescale of about a nanosecond. And it all depends which nuclei you look at and in which environment. Chemical exchange is probably one of the subjects that will live for many years to come. There is currently much attention paid to chemical exchange in proteins and also in DNA, for it has been found that the well-known double helix is not as static as it appears, and that in fact there are many exchange processes that are worth studying in large biomolecules. I thank you for your attention.